Okay. Welcome to Data is a Four-Letter Word. I'm Henry Goffin. This is Paul Dubois. And we're going to be talking about Double Fine's Brutal Legend engine and how it works, how it deals with data, and why we feel like it was successful. Bit of background. In 2005, Double Fine just come off of Psychonauts, and the company is wondering where to go. And the new design for the next game is going to be a large open world. It's going to take a few years to build, so we're targeting next generation consoles. So what do we need? We're going to need a content pipeline that can deal with a lot of next generation quality data. We need a streaming open world engine, and we can't really find anything suitable looking around, so we're going to need to build it from scratch. And whatever we build has to be low maintenance, low impact on the artists, but also simple for the engineers to build, because our platform team is between 3 and 5 people. There's not a lot of public information on how to build a streaming open world engine. Data management isn't really a hot topic at the moment. At GDC, people are talking about soft shadows, they're talking about behavior trees. They're not really talking about how to build your next-gen open world engine. So we don't really know what we're doing. So what this talk is going to be is the talk that we wish someone had given us in 2005. We think it's still relevant now, because the lessons we learned and general techniques we used are very flexible, and we feel like we'll still be using them years from now. We're going to give a very brief glance over our generic asset pipeline. We're going to talk about runtime techniques we use to load and unload data and decide what data should be loaded. We're going to talk about the low-level scheduling of how to get that data from the optical drive as quickly as possible, and the key concepts that power all of these things. It's a shared solution that we call the Static Asset Reference Graph, or REF graph. The REF graph is pretty much the key to everything we do because it let us not know what we were doing most of the time. Now, the talk is going to be mostly the engineering concepts and the general ideas of how the REF graph powers the other 3 points on this slide. So it's not really about artist workflow so much as engineering concepts. The talk is a little bit dry. There's not a lot of pictures. Sorry. I'm Henry Goffin. I joined Double Fine in mid-2008, pretty far along Brutal Legends development. This is Paul.
Hi, senior programmer on Double Fine. I'm responsible for the design and implementation of the I/O scheduler, I/O manager. I also work with a lot of the offline systems that we're going to talk about today.
I worked more with the late additions to the system, such as mesh and texture management and tuning of the I/O scheduler. Brutal Legends started work in 2005 and it shipped in 2009. It only took us about 4 years to figure out what was going on. It's a blend of action, strategy, and open world elements, all unified by this crazy heavy metal theme and a really wicked story. It's a streaming open world in a single-player campaign that covers 64 square kilometers of terrain that we divide into half-kilometer tiles. The player is free to travel across the world without stopping at fairly high velocity, so our engine needs to be able to handle all this data and manage and load it efficiently without stalling or causing the player to have to wait. The 64 square kilometers covers an awful lot of data. We have 100,000 shipping assets on the disk. They're divided into about 100 different data types, everything from cutscene descriptions to visual effects and effect tables, hit reactions for what happens when units get into combat, tile data for height fields, visual types so we can categorize our assets, weather effects, and gameplay tuning, the works. We break these down into 4 general categories: audio and video, meshes and textures, trivial assets, and everything else, which is the bulk of the talk. Audio and video, we used external solutions. We consider them largely outside the scope of the engine, but we do want to make sure that whatever solutions we're using aren't interfering with what we're doing for our own gameplay data. So we have to reroute all the file I/O through our own core systems. We'll get back to how we do that towards the end of the talk. Meshes and textures are another special case because the client isn't really the game. The client is the GPU. And so they're managed exclusively by the rendering system, and we'll talk a bit about that later too. Trivial assets are anything that we consider small enough to not care about. There's a lot of them. There's about 10,000 trivial assets in Brutal Legend. Most of them are under 200 bytes large, so the total sum of all of them is still small enough that we don't really care. So we just load them all on startup and never think about them again. But everything else, animations, collision data, navigation info, pathfinding, you name it, all that stuff has to be dealt with at runtime. And we don't have a lot of time to solve individual problems, so we want a simple implementation that can apply to everything. So we went with the simplest possible implementation. Data gets loaded when you ask for it, specifically, and data gets unloaded when its reference count hits 0. And if the game asks for an asset that isn't already loaded, and it needs it right now, the game will just stall until the asset is ready. That sounds like a really bad idea. It lays a lot of the burden on game code, probably. Like, you're going to have to manually ref count individual assets, you're going to have to manually preload, you're going to scatter a lot of data management throughout your entire code base, and we don't want to do that. We also don't want to have to think about individual assets because there's dependence assets. If you have a skeleton that needs access to, say, a bind pose and the mesh, then you might try to preload some of them but not others and discover later at runtime that you need more data. So finding the dependencies at runtime is very difficult because you want to preload ahead of time, but the data is not ready to examine for dependencies until later. So the question is, what do we really want? What do we want the system to provide? Like, how is it going to preload things before we know what we need to preload?
So before we answer that question, I have to take you on a short detour through our asset pipeline. I'm just going to go over very quickly the high-level concepts, and then we're going to discuss two of the key data structures. So we have, at its core, a type-agnostic asset system. The agnosticity means that it's very easy for programmers to add asset types to the system. This is important in turn because it has to be easier for the programmer to use the asset system than to use raw file system routines. We don't want anyone doing a raw fopen and fread. That's really going to destroy the performance of our I/O manager if we don't have complete control over where the position of our optical disk or even hard disk head is at all times. We also want to make sure that all our data formats benefit from shared infrastructure for processing, compressing, loading, and packing. And this is also important to extract metadata from our assets as it gets processed. Additionally, we used one file per asset during most of our development process, all the way up until the very end. That makes implementing workflow features like hot reload very easy. And we just figured that we would deal with the packaging problem later. Obviously, we couldn't ship with 100,000 files scattered across a very deep subdirectory hierarchy. But we didn't worry about it until we had an inkling of what the solution was going to be. So within C++, all asset data is referred to using a smart pointer class called rsref. It refers to platform-optimized data in a standard container format. And the API is fairly simple. We call get, and then after some time, after the data is loaded, we return the programmer a const t star. And then to the artist, they do most of their work in a DCC tool, Maya or Photoshop. They export into some easily processable platform-independent format, say a Collada file or a DDS. And that goes through an asset conditioning step that we call munging, which spits out a single platform-optimized file in that standard container format. So just looking at that in a little more detail, say we have a platform-independent material file. It's a bunch of text. Maybe it contains some numeric material parameters, some references to textures. That gets passed through a serializer, turned into a format that's very easy and quick to deserialize at runtime. But when that data gets passed through the serializer, that's also the perfect time to sieve out anything that looks like an rsref. And that's what we do. We take those rsrefs that we sieve out, and we store them in a little bit of sideband data. So now we have an easy way of computing every asset that another asset refers to. So just to give some concrete examples of what references look like in our data, this is a Collada file. It's a mesh. And in red there's a material file that it references. And looking at that material file, here are the textures that it in turn references. So we're just starting to build up a static picture of our data. We know this asset points to this asset, and this asset points to a bunch of textures. If we take those in aggregate, we can imagine a web of asset-to-asset dependencies being formed. But that's not the entire picture. We have other sources of references. For instance, C++. We may have a few static special cases, maybe a list of levels, some game configuration data, hard-coded into our C++. We have a prototype system. Prototypes are how we construct objects at runtime. They aggregate C++ functionality with initialization data, and given a prototype, we actually create an actual instance of an object that you can interact with. Here we see a Cole object, and it's referencing a mesh set, the Cole mesh set. We also have references from script code. Scripts can reference prototypes, so instead of just having everything reference assets, we can have references to scripts, and scripts reference other things, or everything referencing prototypes, and prototypes can reference other assets. So this game is creating an instance of that Cole that we saw earlier. And then scripts can also reference resources. For instance, we might have a cutscene that plays when you complete a mission. So if we tie all these references and nodes together, we get a data structure that we call internally the ref graph. Ref graph is a directed graph that contains every single asset that we've ever authored. Its nodes are assets. They can also be those CPP files, the scripts and prototypes that we just saw. And the edges are references between those objects. This is what it looks like, or at least a portion of it. This is our continent. That's the continent level file right there. And I've excluded all the environment assets. So this is actually a small subset. We don't see any of the meshes and textures that are appearing on the continent. It's only a spanning tree with the full lengths. It looks something like this. And apparently there's a lot of sharing going on in the continent. Maybe something a little bit more understandable. Here's our ballista unit in the game. That's him in the center. Those magenta nodes are related to rendering and animation. Up top, we see an explosion effect with some orange physics assets around it, rigid bodies that it throws out when the effect goes off. And then these blue nodes are random tiny assets. They're the trivial assets that we talked about earlier. Here we have a stance file, which is a list of animations that that entity can play. And then the rest of the sphere is all the way there at the back. I'd like to thank Tamara Munzner for making her PhD work available. These graphs can actually be viewed interactively in real time at greater than 60 FPS, even though you have 100,000 nodes in them. It's really awesome work. So how do we use the ref graph? Why is it interesting? Well, we can answer a few questions, like where's a particular asset used? The artists tended to do that a lot, sort of midway through production. They want to replace a particular bad asset or a one-off asset with a shared asset. So this is easy. We can just look at the asset in the graph, look for all the backwards links, and those are all the nodes, probably assets that refer to that asset. Another question is, what assets do we ship? We just need to start with some seed assets, maybe our CPP files, the levels that we ship with, flood fill outwards, and there you have a list of all the assets that need to be put on disk in the final shipping image. Everything reachable is most likely used. Not definitely used. No one's going to enforce that a programmer will use all the animations given to him. But the important thing is that everything that's non-reachable is definitely not used. We don't want any bugs arising from missing edges or even missing nodes in the ref graph, causing the game at runtime to have some reference that we haven't caught, and therefore not find an asset that it's trying to pluck off the disk because we haven't done this computation correctly. So we put a lot of effort into making sure that statically the ref graph is an extremely accurate picture of everything that might happen dynamically at runtime. So going back to that previous question, what do we want? Well, the question we were asking is, what assets do we preload? And the ref graph gives us all the information that we might need to answer that question. So we really want runtime access to this graph. But the problem is that in its raw form, the ref graph is unsuitable for runtime use, and I'll tell you why. The first reason is that we don't care about the topology. Perhaps we have a mission which refers to the Druid proto, and the Druid proto refers to the Torch proto. Torch proto refers to the Thud effect, and on and on. We don't care about any of that. All we really care about is the fact that they're all part of one conceptual unit. We don't care about the ordering or the traversal order or any of those links. We just want this bag of assets to be connected to mission 2 somehow. Now, the ref graph also contains not enough information for our purposes. For instance, Mission 2 refers to that Druid proto and everything else we saw. It also refers to huge.cutscene and maybe a lot of other cutscenes. So when we start up this mission and preload it, we may have a bunch of cutscenes that we're not going to play at all. We absolutely do not want that 20 megs of animation up to that could come with every single cutscene. What we would ideally like to do is start preloading the animation, all those animations and all that cutscene data, perhaps a second before we start playing that cutscene. Enter the concept that we call clumps. So a clump is our name for the data structure that we use to condense all the information that we need from the ref graph and throw away all the information that we don't. We pre-traverse the ref graph in an offline process and apply domain-specific traversal rules that help us get rid of all those edges that we don't really care about or don't want. We flatten that resulting subgraph into a set, and instead of just calling it set of rsref, we call it a clump. Set is a really overloaded term, and clump indicates the relationship that these assets have with each other. They're part of a single logical unit. And I'd like to emphasize that a clump is actually not the asset data itself. It's just the set of references to the data. So some examples of particular traversal rules. Here's a systemic rule like the one that we saw earlier. Mission refers to the cutscene. We don't care about any of the cutscene data. So when we're traversing, we just kill those links and take what's left over. And then an example of a special case traversal rule. We have a main character. His name is Eddie Riggs. He has a guitar that he can play guitar solos on. And when he plays the solos, they produce magical effects in the world. And the one called Call of the Wild in particular summons beasts to his side to help him fight. Now, one of the problems with this from a ref graph traversal point is that he can summon any one of a number of animals, depending on how powerful he is when he plays this guitar solo. Anything from a lowly porcupine to the massive hexadon. And we absolutely do not want every single animal that he can summon to be loaded up into the world just by virtue of him existing. So that's another link that we cut, and we take what's left over. So to recap, a clump is an unordered, partial traversal of the reference graph. It's not a partition of the entire graph. They can overlap, and they very often do. A clump will start at a node corresponding to a runtime decision, and that's something we'll get into in a little more detail later. And they stop at edges also corresponding to runtime decisions. For instance, which cutscene do I want to play now, and when do I play it? Which animal do I want to summon? And then here's another silly picture of how I think of clumps in my head. So a clump is a spanning subtree of the graph. I represent that with a triangle. We may terminate the traversal earlier. So I have the two examples here. Maybe I terminate the mission traversal right before I get to the huge cutscene. But usually a new clump will be started at that termination point. For instance, we still want to be able to load that cutscene at some point, so I make a new clump there. And then on the right is the Eddie Riggs example. Perhaps the guitar solo is right above those two cyan and yellow triangles. And then I cut off the traversal, and I still make a clump for each of those animals that I might summon.
So since we have all this awesome static data that can tell us how our assets are related, we just want to use them at runtime. We ask the question, what do we want? We wanted to be able to preload things without knowing exactly what the full set was going to be of what we wanted to preload. Clumps are effectively lists of all the reachable assets at any point in time in the game. If we start with a clump for a mission, it's going to cover everything that could possibly be referenced during the mission, with a couple exceptions of things that were cut out. And we want to load everything that's reachable. That's a pretty straightforward approach. It's similar to what level-based games do. You simply have a level, and there's a package associated with the level, which includes everything that could possibly happen on the level. So clumps are sort of like level packages, except that they're more abstract. It's not a physical location, but rather it's just some reachability decision that we make by examining the game state and making decisions about stopping our traversal depending on game state decisions that we haven't made yet. About those decisions, all the cut points that we're talking about as we traverse the graph are runtime decisions. They're things that maybe this will happen, or maybe that will happen, or maybe we'll load one of these many things. Those decisions are centralized. There are only a few systems that actually make important decisions about what's going on in the game at any given time. For example, the terrain system is split up into 512-meter chunks. And there's a terrain tile manager, and its job is to figure out which chunks need to be loaded and which chunks the player is headed towards that need to be preloaded but aren't really active yet. And so what we do is we ask the clump system to generate one clump for every terrain tile. And that automatically includes everything that the artists have placed on that terrain tile, all the animations referenced by those things that were placed, all the collision data, all the data that's necessary to actually load that tile into the world. Similarly, the game mission system decides what mission is currently active. And so we can start with a mission and start traversing the ref graph and build a clump for everything that mission needs. Cutscenes, visual effects, and a few other major systems do similar things. And then we have a few special cases like the Call of the Wild solo, but there's only one or two of them. It's generally just high-level, top-level systems that are making decisions that affect which clumps need to be loaded. We have a simple API that these systems can use for just bulk loading everything. We just say, give us a clump, and once we have that reference to the clump, we can call add reference on it, which internally is going to add reference all the data that is referred to by the clump. We can preload the entire clump at once, which throws it all at our I/O system and says, please load this. And we have the query function, is everything loaded? So the tile manager can decide when a tile is ready to be instantiated in the world. Once all the data is resident, it simply constructs all the game objects. The clump data itself is very well compressed because, as Paul mentioned, there's a lot of overlap and there's no topography. Internally, we store it as just a giant list of all of our assets and an index and run length pairs that describe ranges of the overall asset list. We load all of the clumps on startup along with our trivial assets. The total representation of the clumps takes a little bit less than a megabyte. Most of the clients then are not top-level systems, and they don't have to worry about data at all, because since clumps are providing 100% coverage, they're everything that's reachable given the top-level game state. Individual clients don't care. They can assume that any data that they see that's passed to them is already loaded. All the references are already valid. We know that a few core systems can provide 100% coverage because they overlap, essentially. We have tiles that cover everything that's statically placed. We have mission scripts, and mission clumps automatically cover everything that scripts place. Cutscene clumps cover everything that artists can place. And altogether, it provides a wide and overlapping view of all the data in the game. It's also the worst case. Clumps don't miss anything, or when they do, we catch it at runtime and fix the bug, and then rebuild our clumps. Which means that we are always loading as much data as the game could possibly access. It's large, but it turns out to be a reasonable amount still. We consider it a worthwhile trade-off because it keeps the engineering complexity extremely low. However, it does mean that for certain things, like all the animations for all the NPCs in the current 2-kilometer square need to be loaded. We have fairly good animation compression, which sort of mitigates this, but clearly it's not always the best solution for every piece of data. So just to say where we are so far in the talk, we have a way that we automatically extract all the relationships between all of the different assets in the game. It's immensely useful for us for offline reasons. Our artists can figure out where assets are in the world, what can be safely replaced, what can't be touched. We transform that asset graph into clumps, which are sets of references statically. And then top-level systems use these clumps to bulk load and unload assets at runtime. And the union of all the different clumps from all the different top-level assets provides complete coverage of all the data the game can possibly see, with some exceptions. Render assets, meshes, and textures are extremely large. The set of all the assets that are needed to render the current frame is reasonable, maybe using between 90 and 150 megabytes of GPU resources at any given time with what's on screen and what's near screen. But the reachable set of all the different LODs of every unique object for several kilometers in every direction, plus all the animations for the NPCs you might meet during the mission, plus all the mesh data and textures at high resolution, is not reasonable. We cannot load all that data at once. So we exclude it from the clump system. All clump operations ignore meshes and textures, and it's up to the renderer to decide when to load that data. We do it with a fairly simple on-demand system. If the renderer decides that something is close enough to the player, then it's going to need certain meshes. We compute the LOD based on distance and some other factors, and then we request that LOD. If it's already loaded, great. If it's not loaded, we schedule it. Objects that don't come in on time and are needed to render but aren't ready are invisible, and then we fade them in as necessary. We use delayed LOD switching, so if an object is available at low res but not at high res, we'll keep it at low res even as you get close to it until it's ready to switch to high res. The data is stored in a GPU-accessible memory pool that we keep separate from the rest of our game memory. We treat that pool like a cache. We don't bother unloading things explicitly, but instead, only when the pool is full, we take the last thing that was referenced, or the thing that was least recently referenced, and we throw it away. The pool size is about 200 megabytes, so it's much larger than our average working set, which means that we have a pretty good hit rate. Also, the hit rate is helped by our general art design. We use a lot of shared materials. We have a material library. So textures often live in the cache and are found again instead of being reloaded. And also, we reuse assets throughout the world, so we don't have to reload each individual tree from disk because there's probably another copy of that tree already on screen. Now, this does sort of suggest that we might have a big problem with pop-in. If we only load everything when we know we need it, then it's too late. But the LRU cache does a surprisingly good job here for the reasons of asset sharing and just the general artist workflow that leads to a good hit rate. But also, we have some other things working in our favor. World position is continuous. You run through the world from point to point along lines, which means that new data only appears to us along the horizon. Pop-in at the horizon is not really noticeable. It is going to pop in eventually anyway because we have calling distances and far clip plane and whatever. So we find that the difference between if it comes in at the clip plane or if it comes in at the calling distance or if it comes in a little bit later isn't really noticed by the player. We do have problems with teleportation. If you jump to a non-continuous location, all of a sudden we have a bunch of assets that we need to render that weren't visible before and haven't been loaded and aren't in the cache. We generally hide this by fading to black or putting up a load screen whenever there's a large teleport. This is not really seen as a problem with our open world implementation because teleports are strictly controlled. They only happen when the player makes a clearly intentional decision, like I'm going to start a mission or I'm going to enter a certain region of the game that's visually distinct. And so we hide these teleportation events behind a black screen, and we render a frame. We find out what do we need to render at the new location, and we start loading all that data. And once the data is loaded, we fade back into the scene, and it looks like everything was loaded intentionally. There are a few other caveats with a GPU memory pool that I'll just go into briefly. Fragmentation is a big problem. In general, memory fragmentation happens when you load and unload and allocate and deallocate ranges of a large pool without thinking about the sizes of the remaining holes. If you allocate lots of objects and they have large size and indefinite lifetimes, you're going to get pretty significant fragmentation. So what we do is at runtime, we continually repack the data in the pool towards the end of the pool. But doing this from the CPU ends up being very difficult. We realized that synchronizing access to the pool between the CPU and the GPU was going to be sort of untenable. And so we use console-specific GPU memory writes to actually have the GPU do the defragmentation every frame. We spend about 1 millisecond a frame just copying data around and shuffling it towards the end of the pool, trying to keep a large contiguous block free at the beginning of the pool. It's not that bad, but there are some platform-specific issues. Mostly to do with the pipelining of GPU commands and the orders of reads and writes and texture caches and vertex caches. They're easy to catch because you'll be playing through the game and you'll realize all of a sudden that your main character has exploded and his mesh no longer makes any sense. So we were able to figure out that we had platform issues early on in the game. Solving them ended up being fairly in-depth and required more engineering time than we would have liked. You're welcome to ask us about how we did that offline after the talk. Another problem we had was that it turns out that occasionally our pool isn't quite large enough, and our working set under worst-case conditions is larger than the amount of memory we set aside. This resulted in the last-minute addition of a panic mode, where the engine realizes that it's not going to fit and tries to come up with some workaround. The artists, during development, had an on-screen budget meter. They could see how much pool memory was being used at any given time as they flew around and placed assets. But this doesn't account for worst-case player actions. If the player is in the middle of a skirmish mission and summons one unit of every possible type into an army and collects that army all into one place and stands it in the worst possible location in the world, we blow our budget. So the game detects the critical low memory condition and starts throttling new loads. It says, I need to make some memory free before I can load new data. And it just starts down-resing textures left and right. We just take the highest MIP level, the largest MIP level, the base, and throw it away and rebuild the texture header and say, your texture is actually half the size that you thought it was. This frees up a huge amount of memory very quickly, which we defragment over 1 or 2 frames and then resume loading textures. When the danger is past and we feel like the pool memory is in reasonable limits again, we start reloading all the textures that we downresed. This works pretty well. Also, we don't think it ever happens in the shipping game. It was very, very difficult to actually reproduce these conditions. Human testers had a lot of trouble doing it. We had a robotic testing system written by Paul and that was presented at the previous GTC, which we used to create conditions that would force a panic every time. And that was how we made sure that our panic mode was available. We treat it like a safety net. We think that all of our assets fit into memory all the time in the shipping game. But if one player somewhere manages to prove us wrong, they're still not going to notice. So we'd like having that safety net. Audio and video systems are another source of data that we don't use the clumps for. They're externally managed. We licensed solutions that we wanted to pass through our own internal systems for scheduling reasons. Passing it through our scheduler turned out to be intensely painful. But to explain why, we have to talk about what the scheduler is, what it does, and what its problems are. An I/O scheduler in general is just a large queue of pending I/O requests. You throw it a bunch of requests saying, I need to load these 20 assets, and it comes up with the optimal order to load those assets from the disk. We have one scheduler per device. This simplifies the I/O loop and keeps each individual scheduler simpler and easier to understand. And it avoids bizarre platform-specific asynchronous notification mechanisms. We can generally hide everything with a simple API and a simple loop. The optical drive is the device I'm going to talk about mostly because we are a cross-platform game and a large portion of our target market only has optical drives. There is no hard drive in a lot of installed systems. Everything that helps the optical drive will also help the hard drive. So if we do copy data to the hard drive, all of our improvements to the scheduler will still apply. The hard drive is more forgiving, but it still benefits. We went in with some idea of what an optical drive is and what it's going to be good at and what it's going to be bad at. It turns out we were a little bit off. We assumed that optical drives are slow. That's not actually true. The maximum throughput of an optical drive is pretty high. The real problem is seeking. We knew that seeking was bad. We didn't realize how bad it was. It cannot be overstated. Even if you make small seeks, with nearby regions of the disk, your 12 megabytes per second is going to turn to 1 megabyte per second very, very quickly. So the goal of our I/O scheduler was to minimize the amount of throughput we lost to seeking. If we're going to be loading things in large batches ahead of time, as opposed to at the very last second, the main goal is going to be just straight system throughput. So to do that, we use a one-way elevator access system. The drive has a natural forward direction to it. It likes to read data sequentially. And so we try to keep things as much as possible in that sequential ordering. We take the incoming requests and we sort them according to where the data is on the disk. And then we pick, at any given moment, we pick the first request that is closest to where we last requested something. And ideally, it's adjacent. But we do have an additional goal, which is the ability to service high priority requests quickly. Sometimes, maybe for rendering reasons or because of an external system, a request is going to come in that has to be dealt with right now. That trumps all seek considerations. And so whenever this happens, we just ignore position completely and just go for the data. To store all this data in the queue, we use a tree heap, which is a combination of a binary tree and a priority queue all in one data structure. It's pretty nifty. The key that we use for the tree portion of it is the physical location of the asset. And the priority is simply the priority that the game requested. Now, the way that a tree works is that the root node of the tree is always the highest priority that's available in the tree. And from there, you have sort of a binary tree that you can search left and right in to find individual keys. So what we do is we walk the tree to find the next key, according to where we last were, that still meets the priority requirement. And this is pretty much our entire scheduler. When I first came to work at Double Fine, I realized that it was about 12 lines of C++ code. I was kind of confused because I thought that this seems way too simple for what we need. But the concept is actually entirely hidden within the treep. The treep just is the right data structure, and it handles all of the complexity. The loop is fairly simple. We just take the highest priority in the tree. We find the key that's closest to the previous key that still matches the highest priority. And if we can't find such a thing, then we start again from the beginning of the disk. We know that there's at least one asset in the tree that matches the priority because of the root. It's in the tree. So we take that request that we found, we process it inside the scheduling thread, and then we write down that that was the last key that we were looking at, and we remove it from the treep, and we start over again. Now the scheduler behaves best when you throw it a lot of data at once. If you only request one asset at a time, then the scheduler has no choices to make, and you might as well not have it. If you request your entire disk at once, then in theory the scheduler will simply read the entire disk sequentially. So bulk loading large clumps of data at once is the best possible throughput for any given disk layout. It will automatically find contiguous regions and just load that data and use the fewest possible seeks. However, we originally decided that we were going to use clumps and priorities to try and manage how data came in to make sure it was ready on time. Priority changes have a very high cost. It's almost always a seek every time you change priorities because different systems are requesting different priorities and different systems are requesting different data. So the data at different priorities is never correlated with disk location. So the throughput, we turned out that the throughput that we lost to the seeking outweighed the benefits of trying to seek to multiple priorities. So we just don't mess with priority. Almost all of the game uses one priority, which is normal. And there are a few time-critical systems that use high priority, mostly, for example, tile loading. We don't want the player to be able to run into the edge of the world and not have height field data ready. And so the tile system uses high priority. Now, the external solutions that we have for audio and video don't really play well with our scheduler. The initial implementation was just to pause our scheduler when the external system wants to do something, let the external system finish, and then resume our scheduler. This turned out to be completely unshippable. Sounds would always play late. Videos and music would stutter and skip all the time. And we tried to figure out why, and we realized that there were basically only two kinds of poor behavior, but they were rampant. One of the problems was stuttering reads. What would happen is the external system would request a piece of data, do a little bit of processing on it, request a bit of data, do a little bit of processing on it, and what would happen is our scheduler would sneak back in for a couple of milliseconds, start seeking the drive somewhere else, and then immediately have to slam the drive back over to go deal with the external system. This caused delays all over the place. The system has to wait for a seek, and our scheduler doesn't get to do a lot of throughput because we're only reading one asset at a time. It's really just an amped up version of the priority change problem. We're just constantly switching priorities. Read ahead at the external system level helps if we insert a little thing saying, well, if you're going to read 30 kilobytes, you might as well read 100 kilobytes. But it's not a complete fix because the external system still does a lot of seeking, and we just can't account for that. So we came up with a pretty awesome hack. After we deal with one external read request, we assume there will be another one. We just wait 8 milliseconds and do nothing. Most of the time, it's true. The external system comes back in 2 or 3 milliseconds with another request, and we just process it right away. We feel like waiting for 8 milliseconds after every external request is a lot better than waiting 150 milliseconds for 2 seeks. And the other problem is that the systems make frequent requests, and this can lock out our scheduler. The external system, maybe it doesn't request assets one at a time very quickly. Maybe it does it very slowly. Every 100 milliseconds, it'll request one bit of data. But the problem is it still takes about 50 milliseconds to seek to the data and 50 milliseconds to seek back to our scheduler data. So nothing actually gets through. It's not as bad as the stuttering problem, but it still has the same effect, which is to completely destroy our throughput. So we have a different hack that detects and deals with this, which is that whenever a priority level is finally given up, whenever the timeout has elapsed and 8 milliseconds are gone, and the external system hasn't given us anything, we ignore that external system for about 50 milliseconds. We say, you're not allowed to give us new requests for a while. And that guarantees that our scheduler can still make some minimum amount of progress. Now, these aren't really, we can't really blame the external systems as being poorly designed or poorly implemented. It's just a hard problem. There is no standard API for batching up requests. If you're going to design an external system and you need to use a generic API that somebody else can plug into, everyone knows about open, everyone knows about read, everyone knows about close. No one knows about batch open and scatter read. It's not really a standard API. Also, third-party systems aren't really tested with each other in combination. So we end up with systems that work fine on their own, work okay with a minimum game load, but don't work when there's lots of systems trying to play together. This is improving with time and with feedback from people like us who are trying to develop world games, open world games, using these third-party systems. Data streaming 5 years ago, nobody was talking about, and now it's a pretty well understood topic. There are external third-party libraries and platform-provided libraries that can help manage your streaming. Sony's Fios solution for the PlayStation in particular is like a very feature-rich version of our core scheduler. Those two hacks that I described actually resolved almost all of our issues, and so we shipped with our simple scheduler and those two hacks layered on top of it. In retrospect, they're not exactly hacks. After examining them after ship, we're pretty comfortable with what they do, and we don't think they introduce bad behavior. It's hard to formalize exactly why we chose the solutions we did, but it's easy to understand how we got there. We just want to look at the core concepts of, use a treep, use simple scheduling, and look out for abusive behavior. When we find the abusive behavior, we just want to eliminate it, and we eliminate it by eliminating seeks. As long as we minimize the number of seeks that we perform at runtime, we maximize our throughput, and that's really all we want. Now, Paul's going to talk a little bit about another way we minimize seeks.
So the final piece for us to discuss today is packing and disk layout, and this really ties together all of the concepts that we've previously seen. The problem is to first find every piece of data used in the game, then concatenate it into one or more files, but in a way that minimizes the seeks that we need to do at runtime. So some observations that we make before tackling this problem. The game uses clumps to batch load its data. The clump is the unit of granularity of data request. So assets in the same clump should probably be nearby each other, preferably adjacent to each other, so that we can just slam all that data from one end of that portion of the disk to the other without jumping or seeking anywhere inside that clump's data. The clumps are generated by traversing the ref graph, so maybe the ref graph is part of the solution. The first thing that you might think of is, well, why can't we just concatenate all the clumps together? First, I take all the data that's referenced by a particular clump, and then I take all the data referenced by another clump, and don't even worry about any of the overlapping. I'll just duplicate all that data. We'll concatenate those end to end. Now, we're guaranteed that every single clump is contiguous on disk. Therefore, there will be no seeking when we request that clump. Therefore, everything will be golden. But that's fairly untenable, and there are a bunch of arguments I have against it, and some that I haven't put on the slide. The first is that having a one-to-one mapping of assets to particular location on media is very important to us. It's kind of a key simplifier of our system. If we generalize that to a one-to-many mapping, the system would rapidly get very, very complex. And then the second thing is, even if it does fit on disk, Blu-ray can hold a staggering amount of data. We would start drowning in data. I don't know if anyone here has had the pleasure of working with the Blu-ray disk burner, but they're not all that fast. And if I have to write 25 gigs of data every time I burn an image, then I would find another place to work. I would kill myself. So those are just two of the many. So what we do is, instead, we just ignore all the duplicate data. So the first solution I would propose is choose a reasonable ordering of clumps, and I'll get back to reasonable later. And then just pack them greedily. And here's a simple algorithm for every clump in my ordered list of clumps. I just take all the assets that I haven't seen before and then append them to a pack file. And then the trade-off for not having all this duplicate data is that any data sharing will break the contiguousness, the contiguity of my clumps. So here's an example. I have perhaps some Lion White mission data and some Bladehenge mission data, two missions in my game, and I've outlined in red all of the shared data that they have. And where you see headbanger.proto, just fill in everything that prototype also references. So it's just a placeholder for the huge lump of data that a headbanger requires. So I can start packing all that data. And then when I get to the headbanger, it's already been packed, so I just ignore it. And then I pack the rest of it. So we can see that Bladehenge, if I load it up, I'll have to first get headbanger.proto, and then I'll seek over linewhite.proto's data, and then grab the rest of it. Now, this isn't actually what we do. We instead of choosing a reasonable ordering of clumps, we choose a reasonable ordering of seed assets. But we pretty much do the same thing. We do repeated greedy traversals from there. It's pretty much the same idea. The differences are subtle. They're not really important for this talk, but if you're curious about why we do this, you can ask after the session. So just to make sure we understand where we are and why this works, it's because reading contiguous assets is very, very fast. The IO manager will sort them optimally, so we don't really have to care what order we append all these individual assets that are part of a clump to our pack file. We can append them almost in an arbitrary order, as long as they're contiguous on disk. If we append them in a different order than we make the requests, it doesn't matter because the requests will all be sorted internally by the IO manager. So what we're doing is making the clumps in aggregate continuous. So back to this contiguity point. If sharing breaks contiguity and discontiguous data within a clump cause seeks, and if seeks are bad, well, by the transitive property, isn't this bad? Well, it is kind of bad, but we limit the badness. I mean, the worst possible case will be definitely bad. We'll seek everywhere for a particular piece of data. But the more well our data is correlated, the fewer seeks we'll have. If we have two areas of the game that share a significant chunk of data, but those two areas are spatially correlated, maybe the data that they share will already be loaded by the time I get to the second chunk of the game. So we apply some very light heuristics, just the sort of thing that you could brainstorm over lunch, and they do a pretty good job with this. For instance, when we're traversing the continent, figuring out all of the clumps or all the subgraphs that we're going to pack into a particular pack file, we use a space-filling curve. If you're not familiar with the space-filling curve, that's what one looks like. This is a Hilbert curve. This is the one we use. And this curve has a nice property that areas which are near each other in two-dimensional space are likely to be near each other in one-dimensional space. This is stolen from an idea in graphics. In graphics, we used a Z space-filling curve. This one is just a little prettier and harder to implement, but I had as much time as I wanted for processing, so I used that. A curve based on the player's path through the game would probably be better, but it would take a lot more time for some person or some robot to figure out that path and to encode it into some hard-coded chunk of logic. It's an open question how much better it would be. We think it might be better. In practice, what we have right now is actually pretty good, and keeping everything very simple allowed us to move on to other topics. But it's still an interesting question to think about. How much better could we do if we chose a more optimal, or if we took more care in figuring out the ordering of our clumps before we dump them into a pack file? Maybe we could squeeze a little bit more locality out of all of our data. Everything that shares some data will be next to each other, so therefore they won't really have to seek very far to reach the shared data and so on. But the key point is that the data in this architecture, using the ref graph, seems to sort itself. As long as your artists are doing a good job of spatially or not spatially varying their data very quickly, for instance, using completely separate groups of assets right next to each other, then at least the environment data will be very correlated, and it'll be highly sorted and will extract that correlation pretty much automatically when we get to the pack file building time. And in practice, artists do tend to place units that are related to Bladehenge near Bladehenge and not scatter them throughout the world. And they place units related to the Drowning Doom in the Drowning Doom areas, and they don't scatter them in the Bladehenge area. Now, they can if they want, and we don't have to enforce any particular restrictions like, here's an art package, and you must only use this art package on these tiles, and you may not steal some assets from over there. And that lets them do interesting things, like maybe we really do want to use a little bit of the Drowning Doom's assets as a little precursor of what might be coming in store for the player. So the the lack of restrictions that we place on the artists really means that they can concentrate more on building a rich and interesting world. So just to get back quickly on the meaning of reasonable, this is pretty much the entire code, or the entire core of the code of the data packer. So we start out with all the players, and we traverse them fully. So the players get first crack. We're going to be loading the players up front, and we want to make sure that those players load as quickly as possible. So what you see here is the nodes that we traverse up front are going to have first crack at making their data contiguous. So we treat the players as being more important than every other character, so we put them first. And then we just traverse all of the T tree stands for tech tree. The tech tree refers to the units that you can summon in a multiplayer game for a particular faction. And the tech tree refers to all of the prototypes in the tech tree refer to all of their assets. So we can do a full traversal, and that's our character pack file. We can do a similar thing for the cutscenes. The cutscenes also refer to characters, but the characters are all contiguous because the character pack file it's gotten first dibs on that data. So the cutscene pack file tends to only be those assets which are unique to the cutscenes. So we have contiguous ranges for all the characters that the cutscenes tend to use, and then a contiguous range for all of the unique animations in all our cutscenes. So the levels, we do that next using the space filling curve that I mentioned previously. The levels may reference characters, but in order to keep all the character data all lumped in one place instead of scattered throughout our level pack file, I should say, we do that after the characters. And it doesn't really matter that it's after the cutscenes. And then finally, the mission is whatever's left, and then there's some lines after that we don't see that just grab everything else. So just to wrap up, what we presented today is just a little sketch of our asset system and how we extract metadata, how we knit that metadata into what we call the ref graph, and that's kind of the core concept that underlies pretty much all of the data packing and the data loading techniques that we've discussed. We've discussed the pervasive use of clumps, which are condensations of the reference graph used for asset loading, preloading, unloading, and data packing. And we discussed some special case systems that don't use the clump system. And we've talked about the optimization of our inner I/O system. So at this point, we have time for questions. And if you don't want to ask a question, I encourage you to fill out your forms before you go.
10 minutes for questions, I guess?
Yeah. So anyone want to start? We've got a microphone
an open
here in the
mic,
middle.
and you're welcome to line up behind it.
Hi. Maybe I missed it, but how do you update your ref graph? Like, I think it was during the munging stage or something. And also, how do you store it? Is it like stored in a company-wide database or something like that?
So the question is, how do we update the ref graph and where is it stored? So whenever we do a data build, artists will submit unprocessed data, and in automated fashion, we'll process that data and turn it into platform-specific assets. Whenever we do that, we also, as a result, generate new refs, and because we generate new refs, we update the clump file at the same time. So every time we do a data build, it's a fairly quick process. That happens continuously whenever we request a new data build.
It's all handled with Python scripts that are triggered every time someone clicks on a button on a web page, basically.
Hi, I wanted to find out, with the, you mentioned that you had LODs. Are they actually considered separate assets? Each LOD is
Yes,
an asset?
we consider each LOD to be an individual asset. This lets our artists manually author individual LODs and treat them separately. We could have packed the LODs together, but we would find that it would basically double our mesh memory requirements and a few other reasons.
Okay, and then for MIP levels, is it similar, or are they all in one?
MIP levels are stored in a single texture. There's a detail which I didn't mention, which is that we actually have a runtime system that it can selectively load portions of a texture. What we do is, if a texture is requested, we, by default, load it up to 256 by 256, but we don't load anything above that, like a 512 or 1K level. And then as the renderer decides that you're getting close to objects based on a pretty simple metric, we just automatically reload the texture at full resolution. But it's all stored in a single asset on the disk.
Did that impact the seek times much? Because then you have to seek back and get the kind of same data again?
generally does not because of the LRU cache. When you're entering an area with lots of new unique textures you haven't seen before, it does impact the throughput of the system. But generally, hasn't really, because we're only preloading things that are needed soon, but not right now, and the things that are needed right now are the render assets, essentially. It turns out to not be a big problem.
And then one last question on that. Did you use texture atlases, or was it?
No, we do not use texture atlases. We think texture atlases are really fascinating, and we think they'd be a really cool thing to add to our engine. But we just didn't have the manpower or the time to research them and implement them in our engine.
Yeah, one of our teams, I work at Pandemic Studios, and one of our teams used texture atlases as basically a manual process. The artist did it. It wasn't really like creating a bunch of individual textures in that.
I see. No, we didn't have artists author packed assets into atlases.
Okay, thanks. Sorry, Pastor.
One thing I'd like to say about the middle question that you asked about doesn't only reading portion of the texture cause seeks because you're skipping over the end of the texture. The hardware actually has a pretty buff read-ahead cache, so even when you're not reading, it's still reading. So skipping over a little bit of data is actually not that big of a deal.
Yeah, a small forward seek is about the same as reading the data in the first place.
What's the impact of split screen on your system?
Split screen is an interesting problem. We do not support it. We felt that it would add an unreasonable burden on the engine implementation. But it's true that if you have two players moving through an open world, you have to keep track of two sets of usable data, two sets of reachable data, and it basically doubles the workload of your engine. We simply didn't want to deal with it, so we didn't.
I can't think of a way that it would impact the core of how the data loading and unloading would take place. We would still probably do everything through clumps and LRU cache.
I was wondering if you tried or considered using a profile-guided optimization for the layout, keep track of what's been loaded and feed that back into the layout.
I'm sorry, what kind of optimization?
Profile-guided, where you keep track of
Oh, right. So the question was, did we consider using a profile-guided optimization? And I tried to sort of hit on that point in passing. You know, it's an open question whether or not a better ordering of seed assets or clumps would produce a measurable difference. And, you know, as an example, I would give predicting the player's path through the world, or using data that we might get from our bot. And I think that's a really interesting idea. And when we do our next open world games, it's definitely something that we'll consider.
Yeah, it was something that we thought of during development, but we felt that it would sort of be a plus. Like, if the system we have is good enough, then we won't worry about it. And it turned out the system we had is pretty much just good enough for Brutal Legend.
Thank you for the presentation. Question, have you considered applying the streaming technique on network-based streaming, where speed is slower but seek is almost free?
Oh, interesting. That is a really interesting set of different trade-offs to consider, but since we were...
I missed the question.
Oh, I'm sorry. The question was, did we consider streaming off the network? Because seeking could be free, but yeah. I would actually say that seeking might not actually be free, because you still have to have a round-trip time to make a request and a response. And then we're talking about the order of milliseconds there, which... If it adds up and you have a laggy connection, then it might be up into the 50s or so milliseconds to make a request for each individual request, which we're starting to talk about similar to DVD seek times.
And the other problem is the bandwidth. Since we're bulk loading ahead of time instead of for most of our assets, we're really interested in throughput, and the network has much worse throughput.
But that's essentially kind of what we do for running off Target Manager on the PS3. But for a shipping title, it's not really something that's open to us because of platform considerations.
We have time for the last question? Okay.
Hello, really nice talk, thank you. I have a question. How do you identify assets at runtime? Do you have like indices like clamp index and the asset inside of the index? Because your source code, right, is not really littered, but has all the strings, right? And then your assets also refer to other assets as strings. So presumably you don't store strings at runtime, right?
Yes.
So could you explain how you refer to assets at runtime, or is it proprietary?
That is a really excellent question. The question is, how do we find assets at runtime? It looks like asset names are strings, and no one wants strings. So we have a really kind of grody hack implemented by, he left. So we run all the strings through a 64-bit hash function, and we check, but we also sort of hope that we never get any hash collisions. With a 32-bit hash function, you can compute at 100,000 assets. The birthday paradox kicks in. You have about a 50% chance of having a collision. With 64-bit hash, we don't even worry about it. So at runtime, when we open up a pack file, we convert all the asset names into these hash IDs when we register them to the table. And if we just say, I want the asset name such and such, we hash it, we take that hash value and we look it up in the table. And we don't actually use strings at all at runtime except to use that one-way conversion from a string into what we call a GUID, which is not globally unique. It's more like unique to that particular run of the game. Okay, and we're going to have to cut it off now. Thanks for coming. Hope you had a good time.